Hello guys, welcome back. This is lecture 24 of the lecture series Signals and Systems. And in this video, we'll learn about discrete time processing of continuous time signal, where we ended in the last class. We'll see a more mathematical framework, and then we'll take an example of digital differentiator, and then we'll see sampling of discrete time signals. So we have seen sampling of continuous time signals and converting them into discrete time. But we'll also see why sampling of discrete time signals is also useful, and we'll see more about it. And as its example, we'll define two terms called as decimation or downsampling and interpolation or upsampling. So this is also called as downsampling, and this is upsampling. So let's get started. So in the last video, we left at discrete time processing of continuous time signals. And I also showed the signal flow. So we first have the continuous time signal xc of t, and we have a continuous time to discrete time conversion. And then here we have xd of n, the discrete time samples given by xc of nt. So here t is the sampling frequency. And then we had a discrete time system. Discrete time system. So let's say this as a impulse response hd of n. So this will give me yd of n, the output discrete time samples, and in terms of the continuous time output, I can represent this as yc of nt, and taking this through a d to c conversion. I will get my output yc of t. So this is what we discussed. And here again the frequency sampling time period is taken as t. So now let us look at each block individually. Okay, the first is the continuous time to discrete time conversion. So in this, the block diagram is this way. So xc of t is there. I first do an impulse train sampling, right? And then I have my samples in terms of impulses, which is nothing but xp of t. And this I take it through and convert it to discrete time. So conversion of impulse train to discrete time. So how it is done? It is just mapping. So this will give me xd of n. So it is just a mapping. So all this comes under C to D conversion. And my xd of n is nothing but xc of nt. When I say mapping, it is nothing but if you have xp of t like this 0t, 2t and so on. So we'll have my xp of t this way. So this is xp of t. So I map this to xd of n. So here I'll have 0, 1, 2 and so on. So at 0 I'll have this thing 1, 2, minus 1. So whatever is the value at 0 and the integer multiples of t, I map it to the integers itself. So now let us try to get a mathematical relation between them. So we know that our xp of t is nothing but summation n equal to minus infinity to infinity xc of nt delta of t minus nt. And then if I take a Fourier transform of this, so I'll get xp of j omega is equal to, so we know that delta of t minus, let me say t naught, my Fourier transform will be just e power minus j omega t naught, right? So similarly, if I take it here, it will be n equal to minus infinity to infinity xc of nt e power minus j omega nt. Okay, so let me call this equation 1. Now for xd of n, the Fourier transform, discrete time Fourier transform, right? Discrete time Fourier transform. So this one is continuous time. So I'll have xd of e power j. I represent omega by using this capital omega. So my xd of e power j omega in terms of xd of n, we have the discrete time Fourier transform formula as this. So n equal to minus infinity to infinity xd of n e power minus j omega n. So now if my xd of n is nothing but xc of nt, right? So I am going to substitute that here. So xd of e power j omega is equal to summation n equal to minus infinity to infinity xc of nt, right? E power minus j omega n. So this I call it as equation 2. Now try to compare equation 1 and 2. xc of nt is same, and we have a e power some factor, and the only thing changing is omega t is replaced with capital omega. So my omega t is replaced with capital omega. If I want to represent omega in terms of capital omega, I can replace it with capital T. So what will I get? xd of e power j omega is nothing but xp of j omega at omega equal to capital omega by t. So which is nothing but xp of j omega by t. So this is the relation we get between the discrete time samples and the impulse train samples. Now if you have to relate it back to the continuous time x of t, so we know that xp of j omega, this was written like 1 by t summation k equal to minus infinity to infinity xc of j into omega minus k omega s, where omega s is the sampling frequency. So we already saw this in the previous lecture that when we sample the continuous time input, we get shifted. The frequency response is like shifted by omega s in the frequency domain. So if we now substitute this here, we get xd of e power j omega is equal to 1 by t summation k equal to minus infinity to infinity xc of j into omega minus 2 pi k by t. So this omega is omega by t and omega s is 2 pi by t. So I have taken t common out. So we all know that for discrete time the frequency Fourier transform is going to be periodic with period of 2 pi. So here also we can observe that periodicity coming in. So let us take an example. So let's say my x c of j omega is band limited to something like this. So this is with omega and the highest point is having a value of 1. Then my impulse train sampling of this would be, we'll have a scaling of 1 by t right? If I sample it with t and I'm saying it is sufficiently, the time period is sufficiently smaller and the omega s is sufficiently larger. So my omega s is 2 pi by t. So here again I'll have this thing. Similarly on minus 2 pi by t also I'll have this. So this is omega. And this will be xp of j omega. So this is 0. So now xt of j omega, e power j omega, how it will look like? This 2 pi by t, it will just scale down to 2 pi because it is 2 pi periodic. This one we can see is 2 pi by t periodic. So this will be omega xd of e power j omega. So j 0. It's just kind of frequency scaling. Or this will be 2 pi. And the amplitude scaling will still remain at 1 by t. Okay. So this is how it will look like. So next step is discrete time processing. So here what I have xd of n and I have a discrete time system and then I'm going to have yd of n. So this I can call ht of n, or in frequency domain I can call it as ht of e power j omega. So my yd of e power j omega is nothing but hd of e power j omega into xd of e power j omega. So next step is discrete time to continuous time conversion. So, or I'll just call it DC conversion. So in this, if I have to write it as a block diagram, I have yd of n as input to this block. So now I have to create impulse train from this discrete time, just opposite of what we did. So conversion of discrete time sequence to impulse train. So then I will get yp of t. So now again if I pass this through a low pass filter, between minus omega s by 2 to omega s by 2, and the amplitude scaling should be t, right? So then I'll get back my yc of t. And how will my yc of t and yd of n will be related in the frequency domain? It will be same. My yd of e power j omega will be 1 by t, similar to this, whatever x we derived. So summation k equal to minus infinity to infinity yc of what we have here, j into omega minus 2 pi k by t, because this is also operating at t, right? So here you have t. Okay. So now let us again see the full block diagram and try to represent what continuous time frequency response are we going to get, and that we are going to relate it to the discrete time frequency response. So again drawing the full thing. So I have xc of t, I multiply it with p of t, I get xp of t, and then I do conversion of impulse train to sequence, then I'll get xd of n, and then I pass it through a discrete time filter with hd of e power j omega, and then I'll get yd of n, and then I do the conversion of sequence to impulse train. So now I'll get yp of t. Then this I need to pass it through a low pass filter. So then I'll get y of t, yc of t. So now all this operation, right? So if I have to put a box here. So this entire operation is similar to processing a continuous time signal. And for that we can call that frequency response as hc of j omega. Now we want to find the relation between hc of j omega and hd of e power j omega. So how do I do it? I know that yd of e power j omega is equal to hd of e power j omega into xd of e power j omega. But I also know my relation between yd, xd and yc of j omega and xc of j omega, similar to this, right? So then what I will do, I'll write it like that. So 1 by d summation k equal to minus infinity to infinity yc of j into omega minus 2 pi k by t, right? That is what is the relation. Similarly, on the other side, I have hd of e power j omega into 1 by t summation k equal to minus infinity to infinity xc of j into omega minus 2 pi k by t. So I can relate each of this to each of this. So this hd of e power j omega I can take inside. So I have 1 by t summation k equal to minus infinity to infinity hd of e power j omega xc of j into omega minus 2 pi k by t. So if I relate term by term, we can see that it is just a frequency shifting, right? So I can only take the 0 k equal to 0 term and try to see the relation. So I'll get 1 by t yc of j omega by t is equal to 1 by t hd of e power j omega xc of j omega by t. So t will cancel. I want to get j omega here. So I'll replace omega by t with omega. So what happens to this omega here? Omega is equal to small omega into t. So yc of j omega is equal to hd of e power j omega t xc of j omega. So this is nothing but yc of j omega equal to hc of j omega xc of j omega. So xc of j omega is related to hd of e power j omega t by this thing. So hd of e power j omega at omega equal to omega t. So I can also write it this way, e power j omega t. So this is the relation. So you can see that it is directly related. And the only difference we need to take care is the sampling period. And to slightly constrain it, this is not valid everywhere, but only hd of e power j omega t, only in the place where mod omega is less than omega s by 2. And it is 0 for mod omega greater than omega s by 2. So we see the ease of implementing the entire continuous time filter in the discrete time domain. So that is why it is widely used. Okay, moving on, we will next see an example of this and what is called as the digital differentiator. So we know that differentiation we can do in continuous time domain directly, and for that my hc of j omega, the transfer function will be j omega itself, right? And let's say I'm band limiting it, band limited differentiator. So I will call it hc of j omega is equal to j omega for mod omega less than some omega c cutoff frequency, and 0 for mod omega greater than omega c. So in frequency domain, how will this look like? So it will be like this, omega c minus omega c. So this will be mod hc of j omega. And if you see the phase response, it is actually plus pi by 2 for positive and minus pi by 2 for negative. So this is my phase of hc of j omega. So now this implementation in the discrete time, how will it look like? So I need to take hc of j omega and replace omega with omega by t. That's all, right? And t I can choose such that my omega s is equal to 2 omega c, right? Here 2 is sufficient because maybe slightly greater than 2, but for this example we will consider it as 2. So then my t will be 2 pi by omega s, which is pi by omega c. So then my hd of e power j omega will be j into omega by t, and my mod omega s should be less than pi because I'm exactly taking it as 2 omega c. So it will look like this. H of e power j omega, my, let's say this is pi, 2 pi, minus pi, minus 2 pi. So I am having a triangular kind of thing. Then again from here I will need to draw a triangular kind of thing. So in this I am assuming that at omega c this is going to 0. So I can also take it like this way. Otherwise you can see it will add up in this place. So you will have a discontinuity here, right? So that to avoid that I can take it this way. Or I can take only one of them as active. So that will give the correct representation. And my phase response will be so here it is plus pi by 2 and here it is minus pi by 2. Again here it will be plus pi by 2, minus pi by 2 and so on. Again here what amplitude should I consider? At pi it will be pi by t, right? Which is nothing but my omega c. Omega c is pi by t. I can write omega c here. So next we'll look at sampling of discrete time signals. So sampling of discrete time signals are also useful in some cases, which we'll discuss as we go on. But first let us learn the definitions and see the mathematical formulation, okay? So this is again similar. In this case also we have what is called as an impulse train sampling. But here the impulse train is in discrete time. So if we have a discrete time signal x of n, 0, 1, 3. So if you have some signal like this, okay, and this is n, and I will have a impulse train given by p of n here, since this is discrete time. My impulses are also in discrete time. So I will say this has a periodicity of capital N. So then it will repeat every n times, right? So how will this look like? So 0, n, in between everything it will be 0, 2n, minus n, minus 2n, and so on. Only at the integer multiples of n, the amplitude will be 1. So this is p of n. So if I multiply x of n with p of n, I'll call it xp of n, similar to the continuous time sampling case. So then what will I get? I'll only get the x of n samples at n. So I'll get x of 0, and everywhere else it will be 0, and at n I'll get x of n. Again it will be 0, and 2n I'll get x of 2n, and so on. Here everywhere it is 0, so this is like n minus 1, 1, 2, 3, and so on. And on the negative side also, at minus n I'll get x of minus n. Here everywhere it is 0, and so on. So this will be my xp of n. And my xp of n, xp of e power j omega, how will I write? It will be 1 by 2 pi into convolution of my frequency Fourier transforms of x of n and p of n. So x of e power j omega convolved with p of e power j omega. And p of e power j omega, I know it is the impulse train, and its frequency Fourier transform is given by 2 pi by n summation k equal to minus infinity to infinity delta of omega minus k into 2 pi by n. And this 2 pi by n I can replace it with omega s, the sampling frequency. So here the omega s is equal to 2 pi by n. Okay, so now these are like shifted impulses. So it is also impulse train and frequency domain. So if I convolve impulse train with any function, it will be shifted version of that function, and we have a summation. So my xp of e power j omega will be, again this 1 by 2 pi and 2 pi will cancel, so I'll have 1 by n summation k equal to minus infinity to infinity x of e power j into omega minus k omega s. So if you see, it is just saying that it is periodic with period of omegas, but we already know that for discrete time Fourier transform, it is also periodic with period of 2 pi. So this one we have to limit only to 2 pi intervals, because this convolution itself is over 2 pi only. So if we limit that, then what will we get? So this omega s is 2 pi by n, and this is summation of k into 2 pi by n, right? So I'll get k equal to 0 to k equal to n minus 1. Because for k equal to n, it is again periodic with 2 pi. It becomes 2 pi. So I can write it as e power j omega is equal to 1 by n summation k equal to 0 to n minus 1 x of e power j into omega minus k omega s. So let us see graphically what happens. So if I have my x of e power j omega given by something like this, and I already have it 2 pi periodic. Okay, now I have my p of e power j omega. So this will be repeated every omega s. So 0, omega s, 2 omega s, and then I will call it 2 pi. So I can show something like this. So we can have many omega s's. So depending on the ratio, right? minus omega s minus 2 omega s minus 2 pi. And it continues. So now when I convolve these both, and it is only over an interval of 2 pi. So you will take this and convolve it over an interval of 0 to 2 pi or minus pi to pi. Then I will get only these instances. Right? It will not add up and tend to infinity. That is why I am repeating. So now my xp of e power j omega will look like this. So I'll have omega n to minus omega n, and around omega s I'll have the same thing. Around 2 omega s I'll have same thing, and around 2 pi I'll have same thing. But here the frequency, the amplitude is scaled by 1 by n. That is what we need to keep in mind. So around minus omega is also similar. And so on. So this is when aliasing does not take place. So if you see this where it is meeting, it is my omega s minus omega n. So this should be greater than omega n, which means that my omega should be greater than 2 omega n. So this is nothing but my sampling theorem. So you can see here also it is similar to whatever is there in the continuous time case. So if this is not holding true, then we'll see aliasing taking place. So to recover the signal, what we have to do? We just have a low pass filter. I'll call it h of e power j omega. So it will be scaled by a factor of n, and it will be between minus omega s by 2 to omega s by 2. And since this is a discrete time filter, it will be periodic with period 2 pi. Something like this. Okay. So now if I pass my xp of e power j omega through this thing, then I will get back my x of e power j omega. So in time domain, what will I have? I'll have my x of n as the sinc function. So which is sine omega c n by pi n. And I can multiply and divide by omega c. So I'll have omega c by pi into omega c n. This is like a sinc function. And the amplitude also I need to have n. So I'll have n omega c by pi into sinc of omega c n. My reconstructed signal. xr of n will be xp of n convolved with h of n. So which will give me summation k equal to minus infinity to infinity x of kn into the shifted version of this. So n omega c by pi sine of omega c into n minus kn by omega c into n minus kn. So this is again like a sinc interpolation, but this is in discrete time. So it will not be continuous. It will be only the discrete sinc we will have, and it will give me the reconstructed signal. And if my x of n initially itself was band limited, then this will be exactly replicated. So there are many applications of this. So we'll see two such applications called as decimation and interpolation. So decimation, which is also called as downsampling. So where is this used? So if you have a continuous time signal and you initially sample it, but you sample it at a higher rate than omega s. So omega s equal to 2 omega m. Your sampling frequency, let's say, is very much higher. Then it is like you are taking in more information, right? You will have more number of points because you will be sampling very faster at closer instant. So you will have more number of points, which may take up more data to be stored and more space in your memory. But if we know that if omega is just slightly greater than 2 omega m and just equal to 2 omega m in certain cases, we can it is sufficient for us. So this is the best scenario for us. So from this omega s, which is at a higher frequency, we can then downsample the signal. So that is why it's called as downsampling. Downsample the signal to bring it to the Nyquist rate. Okay. So that is one of the application. So in certain cases, we may have sampled the continuous time signal at a rate higher than the Nyquist rate. And then we can sample it again. To bring it to Nyquist rate without any loss of information, right? And in certain situation, let's say this is my xp of n or xp of e per j omega, and then I take it through a filter, and then it reduces to this thing. Now it is no more band limited to omega m. So it is like some omega m prime. Then what I can do is again, I can downsample to bring this omega m again to 2 pi. So this way also I am saving some resources in terms of memory and also in terms of further computations. So this is called as downsampling or decimation, and we'll see the mathematical picture. So we already saw that we are getting xp of n, but my xp of n is such that I'm having 0 here, then I'm having all zeros, 1, 2, up to n, I'm having all zeros, right? And then again 2n, I'm having all zeros. So this zeros I can discard, and I can define a new sequence xp of n, which is equal to xp of n into n. So it only retains the integer multiples of n. So this I'll have 0, 1 I'll have what is at 1, at 2 I'll have 2n, and so on. So this process of retaining only the nth sample is called as decimation. So now let us see the relation in the frequency domain. So my xb of e per j omega is nothing but summation k equal to minus infinity to infinity xb of k e per minus j omega k. And my xb of k I know from this is equal to summation k equal to minus infinity to infinity xp of k times n into e per minus j omega k. And if I replace kn with n, then I'll get xb of e per j omega is equal to summation n equal to integer multiples of n. Right? It will be plus minus 0 plus minus n and so on up to infinity. So here I'll have xp of n e per minus j omega, and k is nothing but n by n. So omega n by n. And since my xp of n is anyway equal to 0 for n not a multiple of n, or not an integer multiple of n, I can replace this summation with xp of e per j omega is equal to summation n equal to minus infinity to infinity xp of n e per minus j omega n by n. And if you see what is this, this is nothing but my xp of e power j omega with omega replaced with omega by n, right? So this is nothing but xp of e power j omega by n. So my xp of e power j omega is nothing but a frequency scaled version of xp of e power j omega. So to see it more fully in the graphical picture, let's say this is my xp of e power j omega, and this is my omega m minus omega m. We'll also see what the x of e power j omega looks like, right? That will give a more formidable picture. So x of e power j omega, I have omega m minus omega m, and this is anyway repeated at omega s interval. So repeated this way, this is 2 pi minus 2 pi, and here also at 2 pi and minus 2 pi I have this. So now what is happening? Now this is expanded by n times, and we know that here from 0 to 2 pi there are only n minus 1 times. So n times meaning it will cover the entire 0 to 2 pi range. So my xb of e power j omega, it will look like this. 2 pi minus 2 pi, and this side also you will have this, and this will be n times omega m, and this will be minus n times omega m, and this factor is anyway 1 by n. So that is going to hold because there is no difference in the amplitude scaling. And sorry, since it from minus pi to pi there is n minus 1 terms, so this should be at pi, minus pi to pi. So this is somewhere like pi minus pi. So this will be minus n omega m, and this will be n omega m. And my whatever is at 2 pi, it will come like this.
Bye.
So this one not to scale, but this is the overall picture. So what is happening? So this was our original signal. If we had just sampled directly at 2 omega m, we would have directly got something very close to this. This pi will exactly coincide. But since we sampled at higher frequency rate, we were getting many more replicas inside minus pi to pi, right? So once we down sample it, then we are getting back to our normal close to Nyquist frequency, and we are getting only one of the replica, right? Or one of the x of e power j omega term inside minus pi to pi, basically an interval of 2 pi. So this is called as downsampling.
Fans.
So for this we already saw what is the use case. So next we'll see interpolation or upsampling. So it is just the opposite of what we saw here. So here what we do is we have x of n. So 0, 1, 2, 3, minus 1, minus 2, minus 3. Now we insert zeros in between them. So we can insert n number of zeros, but let's say for example's sake, I insert only 1 0. So this is 1, 2, 3, 4. This is 0, and this is 6. Similarly, on the negative side, minus 1 will be 0. At minus 2, you will have whatever is at minus 1. Something like this. So minus 5, minus 6. So this will be, let's say, my xp of n. And then what I do, I pass it through a low pass filter. So then I'll get the values at these places. It will just be the average of this kind of thing. So something like this. Yeah? So 0, 1, 2, 3, 4, 5, 6. Minus 4, minus 5, minus 6. So this will be my xp of n, or let's say if I start with xb of n, the downsampled version, I can get back my x of n. So let us see what happens in the frequency domain. So this is in the time domain, right? So in the frequency domain, let's say my xb of e per j omega is something like this. Okay. And at 2 pi it is repeated. Minus 2 pi. Right? So once I interleave, what will happen? I'll get 2 of them. So this is 1. And at pi I'll get 2, minus pi I'll get 3, at 2 pi I'll get. Basically, if I interleave with n zeros, I'll get n replicas in an interval of 2 pi. Here from minus pi to pi, I get only 2 replicas here. So then I take a low pass filter. LP. So then what will I get? So I'll get only this. Again, this low pass filter is repeated over 2 pi interval. So I'll get only this thing. Right? So it is actually shrunken in frequency domain. The way I have drawn, it's not shown. So if it is from omega m, this will be omega m by 2. So this will also be omega m by 2. So this will be my x of e per j omega. This is xp of e per j omega. And at 2 pi also you will have same. So in downsampling, what happened? Your amplitude reduced by 1 by n. So here your amplitude will increase by n times. And since your n is 2, your amplitude will increase by 2 times, n equal to 2. So if this is 1 to start with, here it will become n equal to 2. Okay. So let us take an example to illustrate this, why this is important. So let's say my example, let's say my x of e per j omega is something like this. And this is between 2 pi by 9 to minus 2 pi by 9 and 0. And it is going to repeat every 2 pi interval. Let's call this as 1. 2 pi by 9 to minus 2 pi by 9. 2 pi. 2 pi by 9 to minus 2 pi by 9. So this will be 2 pi plus minus, right? So I am not writing this. So this will be minus 2 pi. So now what I have to do here is, I have to spread x of e per j omega to fill the entire band from minus pi to pi. So I have to just do a frequency expansion by a factor of 9 by 2, right? So I have to scale my frequency by a factor of 9 by 2. But can I do it in a single go just by using decimation or downsampling? I have to basically downsample it by a factor of 4.5. But I can only do it by an integer factor, right? So what I have to do is, I first upsample. So let's say if I just directly downsample, by 4, then what will I get? I will get, this will be 8 pi by 9 to this will be minus 8 pi by 9. So still there is a gap, right? I don't want this gap. So what I have to do? I have to first upsample by 2. Then downsample by 9. So if you see, always when you upsample, there is no possibility of aliasing. No aliasing here. Why? Because you are actually taking the frequency from whatever it is there, and it is like you're increasing your sampling frequency, because you are having a shrinking in the, the frequency scaling is actually shrinking in the frequency domain, right? So there is no loss of information because of upsampling, but only for downsampling you have to be careful. So if you first upsample, then there is not gonna be loss of information. But first itself, if you downsample by 9, so this is gonna move to 18 pi by 9. So then your second band will going to overlap here. So that shouldn't happen. So you always first upsample. So once you upsample, what is going to happen? This is 1 and 2. So 1, what is going to happen? So here it is 2 pi by 9. So here it is going to be pi by 9. And let's say you take care of the amplitude accordingly. So minus 2 pi also, it will be pi by 9 interval. This is plus 2 pi. Minus 2 pi also, it will be pi by 9 interval. So second, you downsample by a factor of 9. So now it will exactly sit between pi and minus pi and pi, because minus pi by 9, downsampling by 9 will expand by 9 times. So it will be something like this. And 2 pi also, it's going to be continuing. And amplitude you can take care of accordingly. Amplitude can be taken care appropriately. So here it is going to increase by a factor of 2, and here it is going to decrease by a factor of 9. So you just multiply it with 9 by 2. So basically multiply finally by 9 by 2. So then you will get back whatever the signal x of e per j omega you require to fill the band minus pi to pi. So to achieve the maximum possible downsampling of xc of t, you also require it to upsample sometimes, because the factor may not be an integer. So that is where upsampling is also useful. So that's it for today's video. In the next video, we'll learn about the last important topic, discrete Fourier series, DFT. So this topic is actually very much asked in GATE exams and other competitive exams, and it is really very useful to know about it. So we'll meet in the next class. Until then, take care. Bye-bye. See you.